Okay, thanks, boys. So, I'll just show you the way I want you to go about doing these questions. So, we have our data set. I've done over on the right my average for each time period, as well as the absolute error. Um, Looking at that, guys, the error does tend to get bigger the further the data gets on. As I said, though, there's not much point attributing that to real life stuff because I have made this data up. But it's hopefully similar to data you guys have. So calculate the gradient of your line. So the change in temperature over the change in time. What does this represent? If I was to put my phone on silent, let's do that now. Whoever that was. If I was to calculate change in temperature over change in time, does anyone want to have a thought as to how I would do it? What would my gradient represent though? Like in terms of practical application of this experiment, what does the gradient represent?
We'll show that like over time.
Yes, it will show that. But what like physical property will that demonstrate?
Well, increasing.
You're on the right track.
Is it temperature?
Okay, what is temperature?
Heat.
Heat energy? And how do we put heat energy into the water?
So
The hot plate? And that hot plate would have had a certain amount of joules per second. Or in other words, it's watts. So essentially, the gradient is going to show us how many watts we were pumping into that over time. So for me, with my data, where would I find the change in temp? Average what? So which one would I do?
highest.
Highest, second, smallest. Excellent. So for us, that's 61.3333. Over the change in time. And what was my change in time? 360. 360. And this is going to equal some amount of degrees Celsius per second. It won't be a big number, it'll be a small number. Actually.
Like it started there, it's under 20.
Yeah, good point. So that's how change goes.
Yeah.
Averages.
Yeah.
Because if we can't really select one trial because we've got to assume that our average is the best measure of our data. And that will measure some sort of degrees per second. Now, watts isn't degrees per second, is it? Per second. What is watts?
1,000 joules.
Yeah, joules per second. Yeah, when people are doing stuff upstairs, it vibrates the fan. It's very annoying. So we could turn that into. Thanks. We could turn that into watts by doing some maths, which I think is one of the following questions.
Yeah.
Yep.
Aircon sort of.
Master, yeah. Okay. I suppose we should probably actually calculate that. Can anyone tell me what the answer is?
You
had one job.
Oh, come on to the jet calculator. It's on. Critical.
So. Sorry? That cannot be right. divided by 360.
0.158 gigafarads. And
I'm going to keep, but 640 divided by 360 cannot be 9 point something. It's got to be a decimal, like 0.0 something. That's what I mean by it can't be that.
I just try to open this.
0.11 I'm going to go with.
That was the other.
Okay, so 0.11. I want to use my value to estimate the specific heat capacity of water. Now, how would we go about doing that, Jerry, guys? Well, that's what the answer is, but we want to use our data. Now, once again, I made up this data. We can't get past that. I made this data up, so we are not going to get 4,200 as an answer. But what formula would we use to find the Q equals MCAT? Q equals mass times thermal coefficient, specific heat capacity, times delta T. We're looking for C. Now, here is our issue, guys. Do we have Q?
No,
we do not have Q. Do we have M?
Yes.
Do we have C?
C.
No, because we're trying to estimate it, so we don't actually. Because we're going to use our results to find it. Do we have delta T? Yeah. Any thoughts on how we could go from here to solve? Because we've got two unknowns. Is there anything we have that we could swap into this? Anything we know we could use to rearrange our equation?
Yeah. Answer the question.
You can. How could we use the gradient though? You're on the right track. I know that I'm just going to use 0.11 equals the change in time over the change in temp, delta T. So I should use time up here. And the change in time is really a measure of what? And I just said it. It's really a measure of like how many watts have been put in. What is a watt? It's how many joules are going in per second. So change in time is really a change in joules, isn't it? So could I then therefore say that 0.11 is really the change in joules or the change in Q over the change in temp? Oh, sorry, time? No, delta T is temp. What am I on about? Is that an accurate statement that delta time over delta temp is really the same thing as delta Q over delta temp? Because there's a direct correlation between time and joules because we're putting a consistent amount of joules into it. So can I then say, well, if I divide over here this side by delta T and divide this side by delta T, we then have Q divided by delta T equals MC. You see the link between Q over delta T and delta Q over delta T on the right there?
Yes.
So it's actually a direct relationship between the two of them. our gradient, we can then, without knowing what Q specifically is, we know what Q divided by delta T is, and it's our value 0.11. 0.11 equals MC, and I believe our mass was 200 grams, wasn't it? 200 mil? 250? I don't know. From there, we could rearrange. Now, as I said, guys, I made up this data, so it's not going to give us 42 because I didn't have a real data set to work with, so I just guessed. But if we had to use real data, we should theoretically, if we've done a good experiment, get a number somewhere near 4,200. This one would give us like, well, let's see. Let's actually do the mass, I suppose. So divide this side by 0.25. Divide by 0.25, which will give us C equals. I got. Four, three. There's something I've forgotten to do because it should still be in the realm of similarity.
0.1 equals Q over the.
Yeah, but that doesn't really matter. Because 1 watt is 1,000. So yeah, you times that by 1,000.
Yes.
Which would. Which, yeah, would get closer. Anyway. I'm going to skip question 3, guys, because basically similar to what we just did there. The only difference is that we use our known value of the C, so 4,200, rearrange it, and find what Q would be, and you're done. Question 4, predict the amount of time it would take to reach a temperature of 92 degrees. Does anyone have any thoughts? How might we do this? Use your gradient. Use your gradient. You're all over this, Damon. So, are we assuming this is a linear relationship? Is putting heat into an object a linear relationship?
Yeah.
Unless it changes state and then it stops being linear. But for us, we're not getting above boiling point, so it would be linear. So linear means we have... Yeah, I just explained why. It's very similar to question 2. And because these ones are based around like real data and I made up data, there's not much point going through another made up data one. So linear has a graph of y equals mx plus c. We know our gradient m is 0.11. What would my starting value be? C.
22.
22. That's it. Because that's what at time 0, our y-axis is 22, according to the average. And then we want to know at what time it is 92 degrees. Where would we put the 92? Would 92 be our x value or our y value?
Y.
Y value. That's right. Sub in y equals 92. 92 equals 0.11x plus 22. At this point, guys, it's become a maths problem. The question, predict the amount of time it would take to reach a temp 92. So at this point, guys, it's a maths problem. You just got to rearrange that. I'm not too fussed about rearranging it because I want to get on with today's lesson, but that's the way you solve that problem. There are other ways as well. One way you could do it is you could say, well, at 360 seconds, the temperature is 61.3333 degrees. And then you can say, okay, well, I know that each second my temperature goes up by 0.11 according to my model, according to my gradient. So therefore, I just need to find the difference between that number and 92, divide it from there, find your answer. But yeah. Any questions, guys? Oh, let's get started with the actual topic for today, which is we're moving on to the new topic. So we're done with heats. Done and dusted. We'll do some more revision stuff around it, but we are going to start looking at the next topic. So there's one more topic that will be on your exam, and that's to do with radiation. So to look at radiation, we're going to have to look at the way atoms are.
No. It's 1+3.
What am I looking for? Oh, that's interesting. Okay. So guys, I want to power through this, give you guys a chance to do some problems. On assembly, do they say anything about splitting the lessons this morning? Why would they? Let's just lose 20 minutes from this class every week. It's great. Okay, we're going to be looking at the nuclear model of an atom. I'm assuming this is old hat for you guys. You would have done this in science in junior. I'm imagining, you know what an atom is like. Protons, neutrons, electrons, blah, blah, blah. Cool. So, thanks, guys. I want to blitz through this, but that requires 100% attention. So, atoms are part of the nuclear model of matter, where matter refers to physical substance. So it has to have a mass, occupy space. So all the things we're going to be talking about have mass, occupy space. Modern understandings of physics think that there are not everything either has mass or occupies space, but that's so far above year 11 physics that we're not going to touch it. So what's an atom? Does anyone want to tell me what is it made of?
Atomic
stuff?
Right.
That is a great answer that perfectly answers the question without giving any detail whatsoever. Yeah, protons, neutrons, electrons. There's other bits and bobs in there as well, but the stuff we care about is protons, neutrons, electrons. So, which bits make up the nucleus?
Protons, neutrons.
Protons, neutrons, and then the electron just circle around the outside. Cool. So, proton, subatomic particle, same mass as neutron, and a charge of +1. So, protons are positive, electrons are negative. They are significantly lighter than a proton and an electron. Much less mass. Neutron doesn't have a charge, and the nucleus is the center. Has 99% or so of the mass of the atom. So that diagram on the right, guys, that should be very familiar to you. I'm hoping, at least. Very familiar. What atom, or what element rather, would that one be? 4 protons.
You've got no idea. Hydrogen.
Hydrogen, helium.
Boron.
What's the third one?
Beryllium. Boron.
Lithium.
Do we still have one in the back of it? It's the left one.
Yeah, it's in your...
Helium. We used to have a table in this thing.
You've got it on your formula book. There you go. Okay. Number of protons in an atom determines its name. So any atom with 3 protons, regardless of how many neutrons, electrons, etc., will be the same name. Okay. Number of protons is the atomic number. So bottom left is your atomic number. Top right is your mass number, which includes the number of neutrons. And then you have your big element symbol next to it. So your bog standard carbon atom has 6 protons, 12 protons and neutrons together. So its atomic weight is 12, or atomic mass, I should say, is 12. That's comfortable. You know that from, I was about to say primary school, from year 8 and 9 and that. When did you learn about this stuff in science, by the way? Last year, so year 10 stuff. Okay, cool. Okay. You find these in your formula book, guys. So open up your formula books. Gave it to you in the first week. You lost yours? Why do I have a bad feeling that the bottom of your locker is a nightmarish place?
No, I don't. Oh, my God.
Who, after 4 weeks of learning, still has their formula?
I do.
Fantastic.
What? No, I don't. Oh, look, nothing. Okay. Yeah, I got it.
You got it? Can you find your atomic masses, guys?
This is super blue. How are we doing this?
I just want you to find it. I want you to get used to using it and find it.
Correct your mother, sir. Wait, sir. Hey, how much does the photon make? How much?
A photon.
It's a particle
Zero.
of mass.
Yeah, photon is a particle without mass.
Clearly, so there's no atomic mass.
I said nuclear things with mass and that occupy space. But photon doesn't either of those things. Which is why photons can travel through that's why they can, move via radiation. Things can't. Okay. I'm hoping everyone's found it.
Yeah.
Yeah, Wade has. Okay. So simplest atom is hydrogen, 1 proton, 1 electron. The atomic number would be 1. Its mass is 1 U. So we use U to be the number of things in the nucleus. What would the atomic number and mass be for helium? So the diagram of helium over on the right. What's the atomic number of helium?
2.
2. What's its atomic mass? 4 U. So 4 units of mass. Pretty basic. We say protons and neutrons are the same mass. They're actually slightly different. So we've got this mass of protons here, mass of neutrons here. You can see they're very slightly different. And then your electrons are way, 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 way lighter than both. Cool. The number of positive charges, number of negative charges equal. The atom is said to be neutral. More protons is positive, more electrons is negatively charged. So if it was positively charged, we call it a positive ion, negatively charged, negative ion, blah, blah, blah. So if we look at oxygen as an example, balanced oxygen is just whatever. Oxygen, the -1 charge would be called O negative. If it had -2 would be O2 negative. 1 positive would be O plus. It's pretty basic.
Is there a numeric difference?
Yes.
You said greater than?
Yes. I think in terms of what it would react with would change, and the way it reacts with other things would change. Like if you had a bunch of O positives, it might react very differently in a chemical, an experiment or whatever with O negatives, and certain compounds probably need O positives to be formed. So, rarer compounds probably need a particular ion to work. I'm saying probably because, once again, I'm not really a science teacher, so that's my understanding of it anyway. Cool. So an isotope is a form of element with the same number of protons but a different number of neutrons. Has anyone ever heard of heavy water before?
Yeah.
It's
I don't want to make it.
It's sick.
Water. It's not ingredients making
So so heavy water is when you have, it's called deuterium, which is hydrogen with two neutrons. So obviously, normally hydrogen is one neutron. Is one. I'm having a mental blank. What's the one that's positive? Proton. I kept on trying to say positron in my head. Like, that is not right. Proton. But deuterium then has the proton and two neutrons, so it's triple the weight of a regular hydrogen atom. So if you have heavy water made from deuterium, basically 3 times the weight of regular water, it's really good in nuclear reactions. So going back to your question before, Sam, like deuterium is an example of something where those little differences are really important because deuterium is really, really good at being used in nuclear reactions because of the properties of having those extra neutrons.
How do they make it?
It's found naturally in the deep ocean, I believe, deuterium. I'm not sure. I'm sure you can make it in the lab as well, but there you go.
They're trying.
Yeah, chemical properties are identical. So I just want to remind you guys when we're talking about ions, that's different than isotopes. Because in an ion, what's different?
It's a charge.
The charge. In an isotope, what's different?
So the chemical structure.
Yeah, like the weight, the mass, the chemical structure. So all three of these isotopes of hydrogen. So you have hydrogen, just standard, deuterium with the extra neutron. Then you have tritium, I assume is how you say that. So that's got the 2 extra neutrons. They would react the same. So if you put them through a chemical reaction, regardless of the number of neutrons, it's going to react the same. However, physically they're very different. They express differently. I believe it is the reverse for ions, that ions will present the same physically, but they will chemically react differently. If that makes sense. So the charge would be the condition of how they react, whereas the weight is the condition of how they express physically. Cool. So looking at hydrogen, this is the way we'd write the different isotopes. So hydrogen, 1 proton for a total weight of 1. Deuterium, 1 proton, total weight of 2. Tritium, 1 proton for a total weight of 3. Obviously, weighs the most, weighs the least, or has the most mass, I should be saying. Pretty stock standard, guys. I won't dwell on that. So atomic weight is the average mass of atoms in an element as it is found in nature. So stuff like deuterium is found in nature, but it's very rare. So when we talk about the atomic weight of hydrogen, we will look at the bog standard hydrogen atom. Most elements exist as isotopes. Atomic weight is an average. For example, ordinary carbon consists of 98.89% 12 carbon, 1.11% 13 carbon, and a very small trace of 14 carbon. The average atomic weight is 98.89% of 12 carbon, blah, 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 which equals 12.0111 units. So that's called the relative atomic mass or atomic weight of carbon, both of which refer to averages. Now, if we were in chemistry, which we are definitely not, so I never want to step foot in a chemistry classroom, but if we were in chemistry, would this be something we have to take account of when we're like doing experiments and stuff, like which particular, especially depending on the accuracy of your experiment, you want to be very aware of like, I don't want to like calculate my stuff based on, a less common version of the atom. Yeah, so in terms of carbon, only the 12 carbon has has the exact atomic mass of 12. But then obviously they average it with the other ones. Can I get you to do the textbook questions on page 141? And I will pause.